Hello and welcome to Microtrac's free webinar, Quality Control of Road Aggregates Using 3D Image Analysis. If you have any questions during the presentation, please feel free to type them in the question box in the control panel, and we'll be happy to answer your questions at the end of the presentation. A recorded version of this webinar will be available on our website, microtrac.com. Your speaker today is Terry Stauffer. Terry works closely with Microtrac as a particle characterization specialist, and he has over 50 years of experience in the industry. In today's presentation, we'll go over crushed stone types and the different uses, as well as how aggregates are processed. We will review the required morphological properties in depth and the best methods for measurement. At the end of the presentation, we'll be happy to answer all of your questions. And now, without further ado, I turn it over to Terry.
Thanks, Claudia, and thank all of you out there for tuning in. So let's get started. Both coarse and fine aggregate are used for a variety of construction projects. Fine aggregate is usually composed of natural sand, less than 5 millimeters in size, and makes up generally about 20% of the total construction mix. This talk will focus on only coarse aggregate, which is the type that a number of different international standards impose rigorous tests and reporting procedures on. And automated dynamic image analysis is the best way to meet these requirements in both speed and accuracy. The aggregate mining process consists of mining, crushing, and screening. The overburdens removed, then holes are filled and drilled and blasted, and the rock is hauled or conveyed to a crusher operation using either jaw, gyratory, cone, compound, impacting, or roll crushers. Then it goes on to a final screening operation to achieve the desired size distribution. Here we're showing views of the image file displays on coarse aggregate from automated 3D image analysis. More on the method later, but each row here shown consists of different random projected photos of one particle as it drops through the sensing zone. The images are sorted in descending order. The largest length on the left is 69 millimeters. The largest thickness on the right is 31 millimeters. There are a number of preferred geometrical sizes and shapes for construction aggregate. There are published required size distributions per specific regional testing standards, and size affects packing density and general strength and wear of the mixes used in construction. Aggregate should be nearly unidimensional rather than flat or elongated for desired load-bearing strength. They should also have angular rather than rounded surfaces, which enhances internal holding friction in the bed. The manual testing now performed in this industry to measure the required parameters are very antiquated and take an extremely long time to complete, sometimes to the point that they only get run on a weekly basis. Three major standards organizations have published standards for aggregate tests: the US, Europe, and Asia. ASTM standards D4791 and 5821 for the US, the British standard BS EN 933-3 for Europe, and IS 2386-1 for Asia. The ASTM standards include a standard for flat and elongated particles and for fractured surfaces and angularity of particles. The British and Indian standards cover flakiness index, a value very similar to the ASTM 4791 parameter, because it's an indication of general strength of the final highway bed. Plus, for the Indian standard, angularity is measured by a manual voids measurement, and elongation is measured by size. And all three standards list their own but very similar required size distributions as measured on the testing sieves, and which is matched by the PartAn3D calculated sieve size parameter. Aggregate certified standards require measurement of load-bearing strength as flat and elongated parameters, or flakiness index in the British and Indian standards. Angularity, also automatically calculated by 3D image analysis, is an indicator of fractured faces and degree of acute angles per ASTM D5821. Note that they both specify coarse aggregate. The flat elongated parameters are different for conventional mixes and the newer superpave mix already adopted in many areas. But either one can be measured and calculated using automated 3D image analysis, requiring no manual measurements in just minutes compared to hours when done manually. These are gauges that are used for the manual measurement of the flat and elongated parameter. The broader arrows above point to where the thickness is measured for the two different mixes. The narrow arrows to where length and width are measured. Note, thickness is measured 3 separate times, while both width and length are measured only twice. It's apparent how tedious and time-consuming these manual measurements can be when run on representative samples of each size fraction. In fact, these tests and the one required by ASTM 5821 are often done by outside contract labs specializing in them, which puts a lengthy delay on getting the results. Disadvantages of this caliper measurement method: very time-consuming. Measurement can take hours by a skilled technician. They're very error-prone, subject to operator interpretation, transcription, and calculation. And very small, unrepresentative samples are used, whereas every particle is measured in image analysis. The manual flakiness index measurement consists of a series of screening operations per the British standard, which is used throughout the EU. First, the sample is screened on a series of square hole screens, followed by a series of bar screens. See diagrams above for screen sizes. Each square screen fraction staying on the screen, referred to later as a stay value, is then screened on a bar screen with an opening about half the interval of the square screen fraction. The undersized fraction of the bar screen is referred to later as the pass value, which, when divided by the stay value, is the flakiness index for each size fraction. Flakiness index on a scale of 1 to 100%, the higher the flakiness index, the flakier or weaker the stone mix is. Flakiness index for the Indian standard is measured manually on a handheld slotted gauge for length and thickness measurements on a small hand-selected sample from each size fraction. Disadvantage of traditional flakiness index measurements: they're difficult and involve very time-consuming manual labor. They're error-prone by the typical manual weighing, transcription of numbers, and calculations. Fractured particles per ASTM D5821. At the top in this standard, it says a face is considered fractured if it has a projected area at least as large as 1/4 of the maximum cross-sectional area of the particle. a fractured particle is considered to have one or two fractured surfaces. Pretty complicated. A technician judges visually, particle by particle, how many fractured surfaces it has, and the fraction of the number of particles which have one or two fractured surfaces is measured and reported. Disadvantage is, again, this is a very subjective test with a high chance of different technicians coming to very wide differences in results. It's error-prone in visual judgment, counting, recording, and calculating results. It's an extremely slow process, and it's run on a very small unrepresentative sample from each size fraction. These next two slides show how the Microtrac 3D image analysis mode works. The digital camera tracks the tumbling and rotating orientations of each particle as it falls through the sensing zone, and from those multiple individual images, it defines the maximum and minimum size parameters for each particle so that all three axes, length, width, and thickness, are calculated and reported. Here's a short animation of the 3D imaging method. About 30 different randomly projected areas are photographed for each particle. The image with the maximum length is assigned to the 3D length for that particle, the image with maximum width, the 3D width, and the image with the minimum width is assigned to the 3D thickness value. This example shows particles of very different shapes being measured. The sphere, of course, would give the same answer for all three dimensions: thickness, width, and length. This is the set of parameters Microtrac reports for its PartAn product line. Rather than go into each and any detail here, I'll describe in four general terms what they measure. First, of course, is size. We give you 18 different size measurements of each particle in various diameters, lengths, thicknesses, and more. The last three columns are shapes of different natures and are generally expressed as ratios of size parameters. Form factors include 13 different parameters that indicate how closely the particle is to being a perfect sphere, or various aspect ratios or elongations of the particle. Surface roughness parameters are just that. 3 different parameters can indicate the roughness factor of the particle surface. 2 other parameters report the overall light intensity coming through the particle, transparency, and the curvature of the particle as a gradient of light intensity. Interim size parameters are used to calculate some shapes. But don't be overwhelmed. Only a few parameters are used for any one application. Microtrac has designed a pre-screening accessory for use in screening out the fines prior to the analyzer and weighing that weight, adding that weight back into the final calculation. This accessory prevents fines from blocking vision of the coarse aggregate particles. The plus 70 millimeter fraction, the plus 70 micron fraction is the screen size that goes directly to the analyzer for measurement. "3D image analysis measures all 3 dimensions and is available, patented, from only Microtrac. It provides calculation of such unique parameters as sieve parameter, which is a function of thickness and width, thickness to length ratio, thickness to width ratio, flat and elongated, and flakiness index. 3D gives the true sizes of each particle, not the sizes of particles in random orientations. And more accurate shape measurement results because calculated from ratios of size measurements. Here's one of several results displays in the PartAn3D Maxi software. Notice in the graph and table windows, top left and right, that not only are the length and width dimensions displayed as they are in 2D analysis, but the distribution of thickness is also reported. And they're in the size order that would be expected. Length is the largest, then width and thickness. The table on the right lists the numerical data for each parameter. The window in the lower left allows the user to select up to 6 different size or shape parameters to report, and user selectable summary data are displayed in the lower right window. Here's a view of a measurement result of flat and elongated analysis in the XY graph and table. Following the numbers on the graph, call out 1, the black dashed curve, is a cum % finer plot of the actual sieve data size distribution. Call out 2, the red curve, is the PartAn calculated sieve data, and they overlap. 3 is PartAn width, 4 PartAn thickness, 5 is the 1:3 thickness to length ratio, and 6 is the 1:5 thickness to length ratio, both as a percentage of the total sample and both required for the flat and elongated analysis. In the table to the right, columns 4 and 5 display these two thickness to length ratios as % of size fraction. Flakiness index can be measured by only 3D analysis. The ratio of 3D thickness to width is calculated to calculate flakiness index. Results of flakiness index are reported for all size fractions and for the total sample. These are the results of the 3D analysis for flakiness index. The table on the left lists columns on the screen designations and the size in millimeters of square-hole screens used in the first screening operation, and the third column lists the bar sieve sizes in millimeters. All results are given in the table to the right. Square-hole screen designations are listed in the first column below a stay value, which indicates % by volume in those size fractions. The pass column to the right is the list of % passing the bar screens from the stay screen. The flakiness column then lists the flakiness index for each size fraction and for the total sample at the bottom. Thickness to length ratio is one of the parameters measured in D4791, and angularity correlates to the fractured surface parameter in D5821. Here they're both displayed relative to each other in a plot of both parameters. The blue graph is the scatter diagram, with the two parameters plotted in the X and Y axes. Each blue dot represents the location of a particle with respect to those two parameters. Call out 1 points to where any two parameters can be selected to be displayed on either graph. Summary data is listed on the right. Microtrac offers PartAn3D Maxi lab and online process analyzers with a size range of 0.16 to 135 millimeters. The online Pro version provides continuous unmanned operation and sample measurement with turnaround time averaging about 15 minutes, which greatly improves process control response time with the normal increase in both productivity and quality versus having to collect the samples manually, bring them to a lab, and then make the measurement. It's so labor intensive, manual sampling and measurement intervals generally end up being measured in hours, not enough time to prevent processes from going out of control and possibly shutting down. Microtrac has over 200 online image analyzers installed in various processes globally. In summary, all required aggregate geometric parameters, sizes, and shapes can be measured and reported on the PartAn3D Maxi Dynamic Image Analyzer. Representative aggregate samples can be taken manually and then measured and reported within less than about 30 minutes, in contrast to traditional manual testing, sometimes taking up to 1 day. Microtrac's online process model enables rapid control response to stay within tight tolerance of specifications, increased productivity, decreased process downtime, and faster process startup. And that summarizes the talk, Claudia. I'll turn it back over to you for questions and final wrap-up.
Thank you, Terry, and thank you to everyone for attending today's webinar.